Good morning, everyone. Today we're doing limits with absolute values. Now, for the most part, limits, pretty much like usual, just plug it in and see what happens. So for this first problem here, we see the limit as x approaches 2 from the right side. So what we're going to do here, we're going to go ahead and just plug it in, the 2 in, and see if this gives us an answer. Okay, we're plugging in the 2 into the problem. Oh, sorry, -2. And when we plug it in, it becomes a -14. 2 minus -14 is going to give us a -12. Absolute value of -12 is just 12. And that's going to be okay for us. So 12 is a perfectly fine number for us. Okay, so that jumped to another level. Now this is a rational function. And let's go ahead and plug it in and see what happens. When I plug in a positive 5, we see a limit as x approaches 5 from the right side. But we're just going to plug it in and see what happens. So 5, x is 5 now, 5 minus 5, and 5 minus 5. On top, we see 5 minus 5 is 0. On the bottom, we're going to end up with 0, 0 over 0, divides out. And we know that's called an indeterminate. So from here, we know, okay, it's not going to work. We got to try something different. And our goal is to now to remove the absolute value. Now, in order for us to remove the absolute value, we need to separate this, or let's just estimate what that would look like. If I plug in a 5.1 on one side, that's from the right side. Would that be a positive or negative absolute value still? 5.1 minus 5 would give us a positive number. So do I really need the absolute value there? So one of the cool things is that the left and the right side would give us two different possibilities, a positive or a negative version. And in this case, it would be positive because 5.1 is greater than -5. So we really don't need the absolute value. So when I rewrite this without the absolute value, we'll write it in the x form. And so x minus 5 over x minus 5, they actually divide out, leaving me the answer is 1. So what would the graph look like as x approaches 5 from the right side? It would look like 1, a positive 1. Now, as we look at the problem, the absolute value again, like you can't just divide something inside the absolute value and outside the absolute value. So that's why we had to do this move where we would decide, would the absolute value be necessary or not? And since it was 5.1, it's on the right side. This would be necessary. This wouldn't be necessary because it's going to be a positive. So we could write this like we did on our fraction where we took off the absolute value sign. So that absolute value sign can be written off because our 5.1 on the right side was going to be positive. So we can write it as x minus 5 over x minus 5. Now these can be divided because no more absolute value sign. Now looking at our next example, would we have that problem when we're dividing 0 by 0 again? So like normal, let's just go ahead and plug it in. If I say 8 plus 8, so that's a -8 plus 8 is going to be 0. What's 0 divided by -8 plus 1? That's going to be a -7. Absolute value -7 is +7. 0 divided by +7 is just 0. And that's not 0 over 0, so we are good to go. This next problem, we look at, it's an absolute value and a square. So what does a square do to a problem? And fundamentally, the idea in math, it makes it a positive number. So if I plug in the -5 and -5, we still end up with 0 over 0, and we're not allowed that. So what we're going to do here is we're going to say, well, hey, doesn't a square and a absolute value pretty much do the same thing, make everything positive? So we're going to rewrite this now without the absolute value, and we'll see what happens. So let's go ahead and plug in some values to the right and to the left. I put on the right -4.9 because it's bigger than -5. So when I plug it in, -4.5 would make that a positive, right? -4.5 plus 5, that would be a positive. So do I really need the square? And then when I square it, becomes positive anyways. So this will be a positive value on the bottom. So I don't need the absolute value. So when I get a chance to rewrite this, I'll see that the top and the bottom end up being able to divide each other because they don't have an absolute value. Our goal is to rewrite these problems without an absolute value because you can't work with them with an absolute value. And this leads us back to 1 again. Okay, our next question, they split it up for us. We see a 9 from the right and 9 from the left. Now, like normal, our goal is just to plug it in. 9 plus 3 is 12, and 9 plus 3 is 12. 12 divided by 12 is 1. On the left side, plug in positive 9. That gives us 9 plus 3 is 12. 12 divided by 12 is still just 1. And since the left limit and the right limit both agree, yes, the limit does exist because the left side and the right side do look alike. Follow-up question, we do the same thing. We see a 7 here. Go ahead and plug it in. 7 minus 7 is 0. Uh-oh. Let's write that out. So we have a 7 minus 7 over absolute value of 7 minus 7. That's going to give us 0 over 0, which is an indeterminate for us. So we can't have that. We're going to find another way. And our goal is to say, hey, well, if this was a little bit on the left, a little bit on the right, well, what would happen? So let's go ahead and see. Our goal is to divide that out. Now, would we have a plus or minus sign? Let's see. Let's separate it into two different versions. So if I'm looking at x minus 7 divided by x minus 7 without the absolute value, and we'll write that twice. Now, which of these get the absolute value sign? I'm going to write the right side with a negative sign, but when does it happen that we need that negative sign for the absolute value? When the absolute value makes everything positive. So if that x minus 7 is a negative, we need another negative to make it a positive, to force it to be a positive. So when x is greater than 7, 7 minus 7 is always going to be a bigger number. 7.1, 7.2, 7.3. If I plug it in, the absolute value would have been a positive anyway. So we don't need an absolute value because it's positive. Now on the right side, if x was less than 7, a smaller number than 7, let's say 6.9, 6.9 minus 7, and 6.8, 6.7 minus 7, these would be negative. So we're going to force a negative sign there to make that into a positive number. And when I do that, we don't need the absolute value sign, but I have to catch it with a negative sign in front. So let's go ahead and simplify these. Let's rewrite this. So we can rewrite it without an absolute value sign, but we have to write two different versions. X minus 7, and it's going to be positive x minus 7 when x is greater than 7, no absolute value sign needed. And we put a negative sign on the bottom of the second one when it is smaller than 7 because we knew it was going to be negative. We want to force it to be a positive. Now we can simplify these equations now because you can see that they easily divide out now. X minus 7, they divide out. So let's rewrite this. So x minus 7 divided by x minus 7 is 1. And that's when a positive 1 when x is greater than 7. But a negative 1, so when we divide out, when it's x is less than 7. So that's how we're going to fill out. Which, for x's approaches 7 from the left side, that's a negative. That's smaller, so that's going to be negative 1. And when 7 is greater, when x is greater than 7, that's the right side. And that's going to be our positive 1 version here. And do they agree? The left side and the right side? They don't seem to agree. They're different. So what we're going to say is, since they don't agree, their limit does not exist. Okay, for this next problem here, like normal, we're just going to plug in and see if we have an oddity, a problem. So I plug in 7. 7 minus 7 is 0. And 7 minus 6 is 1. 0 divided by 1 is 0. Okay. Remember, our goal is always just plug it in and see what happens. And only when we have an indeterminate there or we have a problem, then we have to worry about it. But so far, both sides, if I plug in 7 minus 7 is 0, we're going to end up with 0. So the graph should look like 0. There is no discrepancy there. If we had a problem, that probably would have been at x is equal to 6. Again, we end up with a square problem, and we said a square and squares will always be positive. So we can, in essence, just say forget about the absolute value. So we can deal with this problem like we did before without the absolute value, because a square essentially makes everything positive. And that's kind of a math trick that they do oftentimes. If you look at different types of proofs, they square things to make them positive, forcing them to be positive, rather than absolute value. You can't do much with absolute value. You get kind of stuck there. So if we write it out, 2 minus 2 over 2 minus 2, that's going to be 0 over 0. And we know if we end up with 0 over 0, that's indeterminate again. So we can write it without the absolute value this time. And they divide out, and it becomes 1. So our value is going to be 1. And it's be a 1 on top, and it'll be a 1 on bottom. Does the limit exist? Well, left and right side, they do look alike, right? So they do exist. All right, our next problem here. So we have, these look a little more difficult, but same thing, we're looking at left and right side and the absolute value. So first thing we should always try to do is just go ahead and plug in that x value as 3 to see what happens. 3 plus 9, and then 3 minus 3, absolute value of 3 minus 3, that's going to be 0 over 0. We end up as an indeterminate. Now because it's indeterminate, we know we're going to try to do something else. Our goal is to get rid of the absolute value sign. So we're going to have to split this into two different versions. So just to demonstrate this, let's say this is my number line, and I'm looking at absolute value of x minus 3. At 3, this would be 0. So let's check numbers on the right, 3.1 and 3.2. And if I plug in these values, this will leave me with a positive number, so I don't really need the absolute value sign. But if I look on the left side, right, as the limit approaches 3 from the left side, 2.9 and 2.8, this would make this a negative value. So I would need the absolute value sign. So knowing that, when I do need an absolute value sign, when I don't need an absolute value sign, we need to make sure we put the negative for the version of our problem that needs a negative sign. So I'm going to go ahead and write it out for us. On the right side, we have x minus 3. We don't need the negative sign there because we know it's going to be positive. So absolute value is gone. On my left side, I need to make sure I include a negative there. I'm going to force a negative because I know it's going to be negative, and I'm going to force it to be positive. So in essence, we're pretending we have an absolute value sign without that absolute value sign by forcing a negative sign on it. But this, again, doesn't happen throughout the whole graph. This only happens when the x value is less than 3. So let's go ahead and write that piecewise function. On the top, we're going to write x plus 9, and then we're going to write the x minus 3, and we're not going to write the absolute value sign. We're just going to write a negative parentheses x minus 3, and this negative happens when x is less than 3. The right side of this problem, we don't need the absolute value sign at all, so we can leave it as a positive version. And this only happens when x is greater than 3. Okay, so now that we got rid of the absolute value sign, we can start canceling out our common factors. And this leads us to a simplified version of the problem, in which if I plug in the limits now, we won't have a 0 over 0 or indeterminate. So on our top, we have a negative x plus 9. On the bottom, we have just a positive x plus 9. Now, if I do plug in 3 here, the values would be totally different. On top, if I plug in a 3, it would be negative 3 plus 9 would be a positive 6. So for the top section again, that corresponds to the top because we said from the left side, and numbers on the left are less than 3. So when we plug in our negative 3 into the problem, negative 3 plus 3, let's rewrite that out. As we plug in our positive 3, becomes negative, becomes a 6. So the left side would look like a 6. Oops, not a 6. A 12. My mistake. The right side, positive 3. We're plugging in positive 3 to our equation that doesn't need the absolute value sign. 3 plus 9 is 12. Then we can go ahead and plug those in. Does the limit exist? The left side says negative 12. The right side says positive 12. Since they don't agree, that means the limit does not exist. No, the limit does not exist. So I'm going to go ahead and graph this for you guys to prove our point. We're going to write the x plus 9 and then x minus 3 on top, divided by the absolute value of x minus 3. You'll see that the graph is totally split. The left side, as we approach it, let me zoom out, looks like negative 12. It's undefined at negative 3, positive 3, but as we get closer, negative 11.9, 11.6, it's kind of hard to see that, trying to get there, 11.7, negative 11.9, and then we're right there at negative 12. It disappears, right? But we're approaching negative 12. On the right side, we're at 12.6, 12.5, 12.4, getting close. As we get closer to 3 from the right side, it looks like it's going to be 12 also. But this time it's going to be positive. So do they agree? Nope. The limits does not exist. Okay, for our next problem here, same exact idea. We have absolute value. And we're asking to see, does the limit exist from the left and the right side? Would they agree? So I'm going to plug in the 3 in. And when we plug in the 3 into it, we're going to end up with 0 over 0. So because it's 0 over 0, we know we're going to have to probably factor out a x minus 3 there. The bottom 0, because 9 plus 3 is 12. 12 minus 12 is 0. So we have to write our two different versions. Okay, we'll write our piecewise function when x is less than 3 and when x is greater than 3. So if I look at the top one, if I look at my right and my left side, 3.1 and 2.9, which of these would be negative? Well, if it was 2.9, we know it's going to be 2.9 minus 3 is going to be negative. So we're going to need that negative sign on the outside to pretend we have the absolute value sign still there, even though we don't. So I'm going to put negative x minus 3, not writing the absolute value sign anymore. We got rid of that. X squared plus x minus 12 factors out to be x plus 4, x minus 3. And if I did plug in a 2.9, that would give me a negative, so that negative on the outside would force it to be a positive as if we still had an absolute value sign there. So we could factor out the factor, we can then simplify this problem to become a little bit easier. We got rid of our 0 over 0. Rewriting the bottom one, in the positive version, we have a x minus 3, and you can see the x minus 3 on the denominator. Those divide out. So we got rid of, again, our 0 over 0. So let's rewrite their piecewise function. We're looking at negative 1 over x plus 4 on the top when x is less than 3, and 1 over positive x plus 4 when x is greater than 3. So you can tell right now the values are not going to be the same at x equals to 3. So when we go ahead and start plugging our values, the left version is corresponding to our top piecewise function, and our right version is corresponding to the bottom because x is greater than 3. It's all the right side of it. So we're going to plug in our x is 3. So when we plug in x is 3, negative 1 over 3 plus 4, that's going to give us a negative 1 over 7. And same thing for the bottom. If I plug in the 3, it'll be a positive 1 over 3 plus 4 is 7, positive 7. So negative 1 over 7 and positive 1 over 7. Let's go ahead and write that into Excel to check our answer. So does the limit exist since the left and right side do not agree? No, the limit does not exist. Okay. Hopefully you found this is helpful. You can message me if you have any more questions.